We present an effective multi-view approach to closed-loop, end-to-end learning of precise manipulation tasks that are 3D in nature. Our system learns implicit 3D representations through sensor dropout from multiple static but uncalibrated RGB camera views. This avoids the challenges in building explicit 3D representations of the world and does not require any camera robot or camera-camera calibration. We observe a number of scenarios where the popular closed-loop single-view setup struggles. As seen here, single-view systems have difficulty handling self-occlusion. But if the agent had access to the additional views shown here, this problem would be quickly alleviated. Single-view robotic agents also struggle from challenges in estimating relative poses between points of interest from a single RGB image. This is especially evident in tasks that require precise alignment, such as the block stacking shown here. From a single viewpoint, it appears that the blocks are well aligned, but multiple viewpoints reveal otherwise. A single view system fails in this case. Since an image is only a partial observation of the state, our key idea is to use multiple viewpoints to capture a better observation of the environment. This is particularly important for precise manipulation tasks. As shown here, this insertion task requires 3D alignment, since the block has to fit into a hole with less than 1 centimeter of clearance. Using a continuous QLearning formulation, our system's observation space is composed of multiple camera views and the gripper's current aperture. The action space consists of open-close gripper actions, relative end effector displacements, and a task termination action to enable closed-loop control for multiple views. We use sensor dropout during training by randomly turning off camera views when updating the Q network. This sensor dropout mechanism significantly boosts the final performance of the multi-view approach and makes it robust to loss of camera views after training. The value of this multi-view approach varies across tasks. When stacking large blocks, a task that can be accomplished without requiring much precision, we see close to 10% success rate improvement from a multi-view system compared to a single-view baseline. We see bigger improvements for tasks with smaller margins for error, such as stacking smaller blocks, and the insertion task, which has less than 1 centimeter of clearance in the placement location. Our system's utilization of a termination action allows the policy to decide for itself when the task is accomplished. This formulation enables recovery behaviors, allowing the agent to react after a failed initial attempt at the insertion task shown here. Then, once the insertion succeeds, the agent autonomously ends the episode. In conclusion, the presented multi-view approach enables closed-loop control policies for precise 3D manipulation tasks from RGB cameras. This approach works well without explicit 3D representations and without camera-camera and camera-robot calibration.